So thank you very much. I'm Marcus. I work on the performance team in XenServer. And here I'm going to talk about distributed tracing the Xen ecosystem. And I think it's important to highlight that. I mean, even though I have a performance background, I think the scope of the work is wider than just performance. I think it's more about complexity, complex systems. So you have usually a component. In this case here, we're talking about Xen specifically. So let's put Xen in the middle of this complexity here. And you have like an ecosystem around them that is using them. And there are two types of complexity that I probably need to worry about here. So you have Xen itself that tries to go complex over time. So it essentially ends up with more features over time. So any system tends to have more features added over time. So we add more, then we retire over time. So this gets more and more complex over time. And also have the ecosystem around it that starts using this component and becomes more complex to understand this around every time, over time as well. So how do you handle this complexity here? And how can you manage it so that you try to decrease costs, make it simpler, for instance, to new engineers to try to onboard the system? So how is it that you have just started in Xen? How do you make it easier for someone to understand how Xen works? And even for seasoned engineers, how do you make it so that over time, when the system becomes more complex and moves over time, even seasoned engineers are able to understand that this thing has moved? So because they may not have enough focus or attention to try to figure out everything that's changing over time. So I think it's important to keep in mind that it's not only about performance here, but about manage complexity as well. That's the problem they're trying to tackle here. And the suggested solution for that is observability with distributed tracing here. So you are focusing on trying to capture features or actions inside the system and try to couple that to something that's observable. So in the example here, we have this specific action that happens, those two lines at the top here. So some abstract action here, but for instance, it could be memory scrub in Xen. So there's a memory scrub, some activity happening in Xen. Or perhaps at the Toolstack level, it could be something like VM.start, for instance. There are activities happening when a VM tries to start, and that takes an amount of time. And when you execute this action, that's something that's user visible, that matters for your system, for your component that you're trying to observe. And lots of things happen inside the system here, like you have a complex activity happening inside the system that's not visible to the user, but that's not important. The important bit is at the top here. We have the action that you care about. Something starts, so there's something that starts here and then something that ends, and that's what I would like to capture, to observe. And the importance of that is that I can then create something they call a set of features associated with my component. So this set of features is something that I try to attach these features to the observables, and because of that, end up with something like a boundary around my components. This boundary is very important because it allows you to determine if whoever is trying to use a system, he has actually executing something inside the system, or if whatever the complex activity happening inside the system might be delegated to something else downstream. And having a boundary here, well-defined, allows you to see if the activity that you're observing is actually it's responsible for delays or problems that you might find in this complex system because of your components, so you care a lot about it because you'd like to fix, or because of something else that the system depends on. So very much are trying to verify this whole system, or simplify it in a sense that are trying to link potential symptoms associated with the actions that's visible, that you care about, with the root cause that's actually perhaps caused this feature to misbehave. So we end up with a situation in which you observe the system, and then you try to, these actions happen inside the system, then try out of these actions, try to infer what is a reason for that observation that you did at the top of the system that you care about. And because everything is interlinked now, you have this link, this green bit here, linking the symptom to the root cause that decreases the cost. It becomes much easier to understand what's happening inside the system, this complex system, or understand or distinguish that the problem is actually not happening inside the system, but outside the system. As a whole. An example here that you might have for Xen, for instance, that you might have different code paths associated, for instance, in using different processors. So you might have functions here that happen Zen is specifically using because it's run on top of AMD or on top of Intel CPUs. Or perhaps even trying to use nested vert. So if I use nested vert, you can think that perhaps there are some features that Zen depends on downstream servers here. And this downstream server is going to be Zen itself. So we have a complexity happening here because nested vert have requests that origin happens in a specific way because I use a CPU. But if it's nested vert, this might end up in an unlimited chain of levels of nested vert here that becomes much easier to understand if you have distributed tracing in your system. So it decreases the cost of understanding this whole complex system that can grow over time. So there's a potential use for that. It's important, I think, to try to distinguish the idea of distributed tracing here and all the different concepts that comes associated with that. So we have logs. That's a very common way of trying to extract information from a system. And usually when we have logs, we have a unique event, like a unique timestamp, and you essentially just try to log because you believe that might be useful in the future. It's like essentially trying to hoard as much data as you can in the hope that might be useful in the future. So it's a lot of data that start collecting. You don't know if it's going to be useful. There's metrics as well that essentially tends to be a summary of some activities. So it's not associated with a specific timestamp, but more like a range, like 1 second or 5 minutes of activity. And you have some CPU usage, for instance, associated with that specific interval, RAM usage. This sort of summarized information that you might want to obtain as well. That's something that you might want interested to observe in your system as well. It's not a lot of data usually because it's like a concentrated summarized version where that's the opposite of logs. It's usually lots of information associated with specific timestamps. And I think that in between them, there's traces. That's kind of a gold lock of not too much information being collected, like trying to hold information or metrics in which doesn't contain enough granularity, but trace seems to be the right zone or amount of data or detail that you may want to obtain about the system, and it contains enough information to try to understand what's going on there. You end up from tracing a sort of, the concept can be extended to distributed tracing. In this case is because you are collecting these activities, and in the parlance of distributed trace activities or actions are called spans. And they always have a begin and an end event associated with them. Therefore, you always have a specific amount of time of execution of activities in them. And they can go across different components or different instances of the same component, like from the Toolstack down to Zen, for instance, and a potential example here, or some UI, or it could be something like a guest executing some activity, like a web server, and this thing is executing actions that is triggering the hypervisor, the Toolstack to execute something on its behalf, like I/O, for instance, and whatever I/O is handled in a different component in here. So it's distributed in the sense that each component is responsible for generating its own data. That's good because that allows you to distinguish or have the delegated activity of generating this data from different teams. So we have some, like the Toolstack team concentrates on trying to generate data for the Toolstack. They know they're the experts on Toolstack, therefore they can generate that. Someone who is as a Zen engineer might understand how to try to instrument or collect the data from them. And they can do that independently, as long as they use a standard to try to connect this information together. And the standard is this thing responsible for having these two components be able to talk to each other. And this goes across many different levels. As if you use a standard, it could be like you have a web services, you have Zen, you have Toolstack, everybody talking about the same thing. Each of these different components collect data in their own way, but they're all connected, interconnected, and can obtain this tree of activity here. And it's able to understand what the whole behavior of this complex system as a whole. I think it's interesting to point out a slightly bit more difference between logs and distributed tracing. Logs, I think you can understand logs when trying to understand the behavior of the system, trying to find the root cause associated with a symptom from these dots here. Each dot represents an event. There are lots of log lines. They are not structured. If you are a new engineer that's starting looking at them. You may want to debug something going wrong, and then you can just see this bunch of lines, this bunch of events, that's dots, that's what you see in front of you, and try to understand what's the problem here, what is the root cause out of this. It's quite difficult for an engineer, especially for a new engineer, and if you have some experience, you might be able just to see, you can split that in your mind, to say, that's lots of bunching can be split in different components inside, for instance, Zen, schedulers, or I don't know, some mappings, or that's easier if you're a seasoned engineer. Just see a little bit better and can try to understand a little bit in more details, or get some extra information that's not easily available from the logs, just because you are a seasoned engineer. And you may try to analyze the source code as well after some effort, and then you see that there's some connection between these activities, these events here that you see. It's still not quite clear what's going on here. There is a problem here, but where's the problem exactly? It's possible to debug and try to find the problem, but it takes time. You need an expert, 2 weeks time, whatever. Therefore, it's not scalable, right? You cannot train all lots of people to look at the logs. These logs tend to change over time as well. So something that you learned last year may not valid in 5 years in the future. It's difficult because if it's documented, the documentation may have changed. So you need to read the documentation anyway. So it's difficult and expensive. And I think distributed tracing helps a lot in this situation, because if you have a problem like that, it's difficult to understand. If you had distributed tracing, things instrument, you'd see, instead of this, you'd see this. And that's how you see how this extra information helps a lot. So now we have the activities captured instead of just events across the whole stack, across different components. And you see that each line here is a different activity. That's in the balance, it's called span. And they're always going to have a beginning event and an end event. And there are concepts of sorts associated with trying to propagate the activity. So have links, these arrows that you see here, across the different components. If something happens at the top level, and usually the definition of something being at the top level is that it's user visible, you care about, therefore it's being captured, the beginning and event for the specific action. And this thing that's at the top here, then when it calls something else in a different component, it passes along or propagates the context, usually just a random ID, easy to create and easy to propagate. It passes this along to the activity underneath it, and this activity underneath it is going to capture its own begin event, its own end event. It uses the context that's being sent to it, understands this as a parent activity, creates its own ID, and passes its own ID down across to the next activity down the line. You see you have different components here with different colors, just to visualize that. But you see here that whoever is trying to understand all the problem here now might see that because of this thing contains these links, this extra information, they might see that, for instance, if the problem is that the total time here is taken, this amount of time, is because most of the time it's being captured by this activity or this activity here. And interestingly, when you look at that in this abstract example here, you see that, oh, look, there's external calls done outside the component. The green bits at the bottom here, these X's here, these are errors coming up. And this thing is just trying to retry, and therefore the thing at the top here is taking a long time to execute. So you are able to see that the problem, errors, functional errors happening at the bottom here, causing a delay at the middle level here, and this middle is then going up and propagating at the top here. And therefore, yes, you can see that it's much easier to try to debug and understand your system if you did that. And not only that, if you have captured this information, you are able to see it in different ways. Like, for instance, instead of seeing this in lots of details, that's used for engineers for debugging, you might be able to see instead the same information or something like that, that allows you to distinguish the behavior of different components. Like the top level could be a UI, web server, whatever. The middle layer is like Toolstack or XenServer or something happening in the middle, DOM0 or some IO, etc. And the bottom layer here could be something like an external NFS device, vendor, storage, or something like that. And then you are able to connect them all together. And if there's a problem somewhere, you are able to see that, oh, look, this is the responsible for whatever is causing a problem at the top there. So what did you do in terms of implementation here for our for XenServer? So in XenServer, we have started implementing these concepts in a new file, trace.ml, that contains the essential library for creating these spans and capturing these activities. And we're using a standard called OpenTelemetry. It's important to use a standard because then you can reuse all of the existing tools around that the standard that allows you to visualize the results or process them further or collect them further. Like we are using the OpenTelemetry in XenServer. Therefore, if, for instance, a UI or something else wants to connect to the XenServer, like for instance, XenCenter or another client, it's just as long as they use OpenTelemetry, you should be able to connect together the tree of activities of this component with the tree of activities of XenServer by just passing along the necessary headers and the requests associated with this standard. So as long as everybody is using the standard, they can communicate, and this tree only grows, and everything becomes visible because everybody is using the standard. This standard, OpenTelemetry, is one of the latest. Everybody seems to be using that. Seems to be like the right one to use. It's open source and contains libraries for several different languages like C#, Python. And an interesting point to make here is I did not have a library for Camel, so I had to create this library from scratch. That's why I have this tracing ML here, and we have put that into the XAPI project, now available for anyone to use if they want to. Contains a data structure associated with this activity that you see on the right side here. So we have begin, end, and we have parent, all of these links associated with them. And an interesting thing to note here is that this seems to be like a novel way of trying to use this sort of standard, because usually the standards used for high-level applications like web servers, they all seems to be something that's almost a standard now to use. Web service, when try to do a request at the level of the application, everybody seems to be trying to use the tracing to try to understand how they behave. But the fact that they're trying to apply tracing in a complex system, which is not at the application level, but at the level of the Toolstack and at the level of a hypervisor, seems to be novel. And that's actually probably one of the reasons why they did not have a library for Okama in this case, which is understandable because Okama is not a mainstream language, but they do not have a library, for instance, for C, even though they have a library for Python, Java, all of these languages that you usually find in web service. So, well, we still don't have a library for C because we did not have to use it. I'm going to discuss this when we go on to them, but we have this template, or example in Okama, which is quite simple, it's small. Potentially could just translate this data structure on the right here to C and just try to start this from the example template that you see in the situation. So, okay, how does that work in XenServer? So how do you enable that in XenServer currently? So we have a new Xen API object called an observer, and you can create an observer to observe XenServer. And you pass parameters to it, like a name is a unique ID. This unique ID is something that allows you to identify across all of the data produced that this data came from this specific observer here. It might be useful if you want to select this out of a lake that has collected all of the information. You just enable, disable, a flag for that. And you can specify endpoints. So when the data is generated, they collected in form of that tree of activities. All the actions at some point needs to be asynchronously sent somewhere else. So we don't collect the data and synchronously send it somewhere else because we don't want to interfere with the behavior of the program as much as possible. We want it to be really quick from the point of view of the component that has instrumented or captured this information. We wanted to create a data structure very quickly, put that in memory, aside in some buffer, and continue on with what I was trying to do. So this should be really quick, and it's quick. And now something asynchronously just lazily collects the information that has been created and just flushes this down somewhere to some endpoint. We have implemented two endpoints here. The first one is bug2. That's just the default XenServer transport mechanism from capturing problems and bugs. So it's written to files in the file system in non-zero. And there's a load of tools around XenServer that captures this information and then transmit that for engineers to debug, etc. So we decided to keep this one because it's a default transport path. But also add a new one for an HTTP endpoint transport. So that you can submit this data as well. So either concurrently in parallel with the bug2 endpoint or specific to the endpoints of both of them at the same time. And an example here on the right side. So when you submit this to a specific endpoint here, in this case it's a Jaeger UI visualization for distributed tracing. It's an open source project, etc. So you submit this and immediately see activities happening inside XenServer. Associated in this case here with VM.start. I'm going to show some examples for different operations. But
this is an example here. You see the top level operation that you care about. There's VM.start at the top here. There's a begin event here and something at the end. And then what things happen inside in different components, XenOps in this case, in XenServer, that is reacting to the request at the top to start a VM and how long these things are taking. And just remind, it's important to remember that it's not only about how long it takes to execute things, but the fact that even something is being executed is important to know about. So there's a feature here at the top, VM.start. I'm capturing this thing is being used. It could be any feature. Sometimes you can have a feature perhaps in Xen, and you have this ecosystem. And if you instrument this feature, you may know that some Toolstacks use this feature. And that's important in itself. Because if the feature is not being used, you can just decide to retire this feature. What's the point of having a feature that nobody's using? And this gives us some indication about that. So you know that this feature is being used, how long it takes, if there's an error, this thing pops up, and it's all connected to different bits, as I was saying, associated with dependencies downstream and upstream. This command line as well, it does have it can specify components, XAPI and OPSD, or in the future we want to implement instrument as well and collect the data for the storage layer, XenStore, XenCenter, and Xen as well, and all these different components. This hasn't been done yet, but it's extensible. Different teams can implement this on their own, and this can all happen in parallel if you want to. And also, in the future, we're going to have something associated. It's called a processor. That's part of the standard. That means that when you collect the data, you may want to process that. For instance, you may want to capture the data from the code, but only submit or flush to this buffer that's going to be processed later. Only performance data or functional data, for instance, of something that has been captured at the top. You may want to be interested in, let's say, in the spans at the top that you care about that's user visible. You may not want to collect at this point in time, for instance, the debug information in the middle, or you only want something that happens at the boundary. So this can be filtered and as part of the standard. There's a language for that, etc. And then you just capture what you care about. Right now we're capturing everything, but there's space for expansion here. And these are the different endpoints, and soon we're going to have a new endpoint associated with this protocol here that is it's used by lots of tools on distributed tracing, and there's an example of an API that can use to try to do that. And this is all linked by using standard headers that you can use to transmit information across. So now, in the future, if you have someone using the XenServer, you pass these headers any tool, you're going to be able to connect your distributed tracing to XenServer distributed tracing by just sending these extra headers. So in the end, I'd like to get this connection, or everything connected here. So I have all of this stuff here connected by these traces. I'd like to see if I can get a tree that contains everything, activities inside the cloud at this level of the app, and connections activities that happen inside XenServer, and this down to Xen and hardware and dependency streams and for vendors or NFS. So I'd like to see if you can get into a point you can see all the activities together, and when there's a problem at some layer, at some level here that care about, this to the user can then track this down to some activity happening inside XenServer. So have here an example of VM.start. At the top here you have VM.start, VM.end, capture the two events at the top here, and event of VM.start Toolstack. Internal activities here associated with plugin VBDs, plugin VIFs, and you see how long these things are taking, and therefore you can justify the amount of time taken to start a VM here. And just quickly, we have an example of, well, just to see how this works. You can have internal tags, you can filter by this information here, and it's useful as someone to try to debug, and it can be automated as well because it's all using some data structure, right? So it can be. There's an example of VM shutdown here. You just figure out by just looking at this that there are some VIFs being plugged sequentially here, one after the other. Potentially could be plugged in parallel, so it can improve the speed, efficiency of this operation here. In the case of VM migrate here as well, you have two streams, like one send, another one receiving. You have this device being plugged and unplugged here. And interestingly, you have two events at the bottom here, so two failures. Then these two failures here did not propagate, and as expected, interesting. But you can see that if there's an error, you can see the error and get a stack trace here of the problem that helps debug. So this error could potentially have propagated. If it had propagated to the top, you'd see this error popping up at the top and across all of the trees and across all the different components. Someone having a problem in an independent component that's not related to XenServer. If they were using distributed tracing, you'd be able to track it down, this problem, to this specific function in XenServer, which makes it much cheaper, right, to try to collect that. And you have, because this is all collected automatically, you have this real-time architectural diagram that allows you to see everything working together across the different components and different colors you see here. So a newcomer can just look at that and say, oh, that's how everything works. And systems engineers can say, oh, after the latest updates, that's how everything is connected now. That makes it much easier for engineers to understand the system from scratch if they just started. And what I'd like to just discuss is, and I'd like to go into more details the session at the end, is how we could potentially just add across this whole stack of distributed tracing something in Xen that would allow us to try to understand a little bit better how Xen works inside, connected to all of the different components in its ecosystem. And the idea here is that we should be able to create a simple data structure associated with each of these activities. It should be really efficient to create because we're interested in creating these structures every time there is an action that you care about in Xen. So what you need here is for each of the actions, which means each of the spans that you'd like to create for this tree, you need two unique numbers, one for the ID of the tree that are capturing, another one for the ID of this span. So like a unique name, random or unique ID or random ID. And we need to capture 2 timestamps as well. So all these activities are quite simple information to obtain. I don't think it should take a long time to generate this data structure. So it should be efficient to create that. But the point here is, when you decide to instrument something in Xen, so you just need to have a function to begin the span or create this data structure, and then to end it, to just put the end timestamp in it. And we need to decide exactly how is the API for how to export the data after. We're probably going to capture that into some buffering RAM, etc. But that's something that's not very clear to me. And if you think it's useful to have that in Xen, just this sort of details is something I think it would be useful to discuss in the session in the afternoon. And where probably would like to start instrumenting with in the beginning. So there are many areas inside Xen that you may want to attempt to instrument, like creating domains, scrubbing memory, MMU activities, or the CPU scheduler, event channels, or ground tables, all sort of things might take some time to execute. You may want to understand how long these actions are taking inside Xen and connect them all together. So someone who doesn't understand Xen, so it's not only about performance, someone who doesn't understand Xen is able to understand how everything works together when the capture as part of the wider ecosystem of activities in Xen. Perhaps hooking that in Xen tracing, something to discuss, I think, later in the afternoon, if you're interested. Any questions about this?
One problem we can face with distributed tracing is timestamp synchronization. Especially you can have in one domain the clock even running at a different rate and things like that. So that's handled by the third-party tools for analysis afterwards.
Yeah. Right. So it's good to have the timestamp somehow synchronized as much as possible. That's not essential because of these connections that you have between the components. You have something that's a little bit offside. It may be possible to reconstruct where they actually happened because you know that they're connected to something at the top. So it's still possible to reconstruct that, though that requires an extra action, an activity that is going to analysis that's going to provide this information for you to try to synchronize them up again.
Okay, thanks.
Mm-hmm. Any more questions?
I am just kind of interested to see how this would work, like if we put something like this in the hypervisor. I think probably what we want to do is start with one particular thing, like basically like as you're doing stuff for XAPI,
yes.
Find one particular thing in the hypervisor that is slow for you, and that we can kind of take it as an example, and just kind of work on an example, like, you know, just one particular thing that we want to look at, add the tracing in that will help us, you know, understand what's going on inside the hypervisor and see how that works, and then we'll have a concrete example
yes.
of how to do the different levels and stuff like that. Because I can see that it could be useful, but also I can see that like trying to pull the and it's nice that they have tools that will do some of this visualization and stuff and things
yes.
for you, but. Also, it looks like it could be quite complicated and add a lot of overhead and this kind of stuff.
Yes. So I think that's the right thing to do. Yeah. So I think hopefully in the afternoon we're going to be able to discuss something that can start with, just to prove the concept inside them. Yeah. Okay, good.
Before diving into Xen, there are maybe some places like libraries like libvchan, for example. I have a concrete case of something like looks a deadlock around vchans, and I had the problem of getting traces that could be some place that's not inside the hypervisor, but we'll still have the problem of getting the traces out and setting up all the infrastructure.
So an interesting property of all of this data that's produced, that is append only, which means once it's generated, you don't need to change it anymore. So you just need to collect it somehow. So you can use RAM, so buffers in RAM, and this thing gets flushed asynchronously to somewhere else. And all of this data is then being collected, larger pools of data until they are persisted in disk or submitted to some external database. So as long as you collect the data somehow asynchronously, so not synchronously with the code, but asynchronously, you kept collecting this data, as long as you can persist them somewhere, you can later analyze and see the whole tree.
Yes. So all the infrastructure is there to support this.
So it depends a little bit on the component. In the case of XenServer, what you did is that you are writing things to the file system as an option. That's what the bug report option does. Or if you use the endpoint, which the HTTP request, to submit this to an HTTP port outside XenServer, then it's the responsibility of that component to keep and persist it and to continue to process this down the line. So that's what you did.
Okay, great.
So you mentioned vChans. I was thinking that maybe we could instrument XenStore, like all the PV device plug and state changes. If we could add some timestamps to those, it might be easier to track down when some device is not plugging correctly, or you migrated your VM and maybe this device is not in a good state anymore. Currently, the way you do that, you look at XenStore access log, but if you could hook that up to what the Toolstack is doing, then we could see, is it like a user-initiated action? Is it a VM-initiated action? So what would we need in XenStore for that? Is it timestamps or this?
So it's distributed trace is more useful if you're able to create an action, define an action, and then you have the begin and end event. So you need to define what we're actually trying to measure here. That's the action that we're trying to find. And then you find this is the beginning event for the action, that's the end event of the action. And when you have these 2 bits of information, you can just submit that as a new span of activity.
Yeah. We can probably do that for the state change, like we have, I think, state 1 and state 4, so you probably have that as begin and end, and we can probably synthesize, maybe just as a proof of concept, and then...
Yes, I think so. Another interesting thing about this is that you can only keep adding into it, instrument more and more code, and this is all being connected to all together. So you don't need to do everything at the same time, but just keep adding this slowly, and this is all going to work out over time. Okay.